Imagine pulling one specific part out of every car on Earth. Not the engine or the steering wheel, the brakes. Without them, a vehicle instantly transforms into an uncontrollable 2-ton missile. To safely stop that mass, you have to tame an enormous amount of kinetic energy. This is the formula for kinetic energy, and the most dangerous part of it is that tiny number 2. This chart illustrates exactly why that square matters. The physics are specific. If you double your speed from 50 kilometers per hour to 100, your stopping energy doesn't double. It becomes 4 times greater. But physics dictates that energy cannot simply be destroyed. So when you stomp your foot down in an emergency, where does all that explosive kinetic energy actually go? The brakes convert it into heat, violent, intense heat. During a hard stop, brake components reach temperatures over 700 degrees Celsius, hotter than molten aluminum. That is the core engineering challenge of every car on the road. Manufacturers have to safely manage and bleed off that extreme heat without destroying the components required to stop the vehicle. For over a century, the foundation of stopping power has been the drum brake. Inside a hollow metal cylinder attached to the wheel, hydraulic pressure pushes 2 curved shoes outward to create friction. It's a reliable design that remains common because of its low manufacturing cost and long service life. But it has a specific limitation. Because the drum is enclosed, heat stays trapped inside. During repeated hard braking, temperatures rise until the friction material loses its grip. You lose stopping power exactly when you need it most, a condition known as brake fade. To solve the heat problem, engineers developed the modern disc brake. By exposing the friction surface to the open air, the system actively cools itself as the wheel rotates. This photograph shows the anatomy of a high-performance disc brake. A heavy-duty caliper mechanism squeezes pads against both sides of the exposed metal rotor. But think about the mechanics for a second. How can a simple push from a human foot generate enough physical clamping force to stop thousands of pounds of rolling steel? This diagram demonstrates Pascal's law in action. Brake fluid is nearly incompressible. When you press the pedal, you push a small piston. That pressure travels equally through the hydraulic lines and forces a much larger piston outward, hitting the brakes with multiplied force. Hydraulics provide the raw muscle, but it is a blind mechanical system. If a driver panics and stomps the pedal, that raw muscle easily overpowers the tire's grip on the road. If you find yourself in an emergency stop, you might have heard the old advice to manually pump your brakes. Today, doing that is unnecessary and often counterproductive. When you stomp the pedal and lock the wheels, the tires stop rolling and start sliding. A sliding tire has less grip than a rolling one, and more importantly, you lose the ability to steer. Even if you turn the wheel to avoid a crash, the car continues on its original path. This photograph captures a Mercedes using an anti-lock braking system to dodge foam blocks during a heavy stop. Instead of locking up, sensors monitor wheel speed. A computer controller actively pulses brake pressure thousands of times faster than humanly possible, keeping the wheels on the edge of grip so the driver can steer. This diagram shows what happens to the rest of the car. When you brake, the vehicle's weight pitches forward. Electronic brake force distribution, or EBD, reads this shift and actively dials down braking power at the rear axle so lighter wheels don't lose grip. And because data shows that human drivers rarely press the pedal hard enough during a real panic situation, modern cars use brake assist. It detects a rapid, desperate foot movement and instantly applies maximum pressure for you. These rapid-fire digital micro-decisions transform raw hydraulic muscle into precision control. By managing the exact pressure at every individual wheel, the car can maximize its available traction to shorten stopping distances and maintain stability. But up until now, this entire process has relied on converting your forward momentum into useless heat. In an electric vehicle, that energy can be recovered. This schematic of an electric vehicle illustrates the engineering behind regenerative braking. When you lift your foot off the accelerator, the car reverses the flow of energy. The motor now acts as a generator, capturing the kinetic energy from the spinning wheels. It feeds that energy straight back into the battery pack. This provides 2 distinct benefits. It extends your driving range, and because the motor is doing the deceleration work, it reduces the physical wear on your brake pads. So when you look at the spec sheet for your next car, what braking technology do you actually need? You don't strictly need 4-wheel disc brakes. For many daily drivers, having modern disc brakes on the front and drum brakes on the rear provides more than enough stopping power for standard road conditions. The absolute priorities you should look for are the digital systems, the anti-lock braking system, and electronic stability control. Every single time you tap that pedal, you are commanding an invisible coordination of physics, fluid hydraulics, and high-speed computing, all working together in a fraction of a second to bring you to a halt. Tell us in the comments, have you ever felt the ABS vibration in your pedal during a hard stop?